Have you ever wondered how engineers measure the flow rate of water inside a massive pipeline without, actually stopping the flow? I mean, you can't exactly hold a bucket at the end of a municipal water main. So let's dive into this explainer and tackle this fascinating engineering puzzle. The brilliant answer to that question? The Venturimeter. It's honestly one of the most accurate and widely used flow measuring devices in hydraulic engineering today. And the best part is, it relies entirely on the elegant, invisible rules of fluid dynamics. Here's our roadmap for this explainer. We're going to cover what a Venturimeter actually is, look at its construction and working principle, derive the discharge equation, weigh the pros and cons, and finally check out some real-world engineering applications. All right, part 1. What is a Venturimeter? Simply put, a Venturimeter is a device used to measure the discharge, or flow rate, of a liquid flowing through a pipe. Whether it's water, oil, or industrial chemicals, this clever device gives engineers the precise flow rate without disrupting the whole system. And how does it pull this off? Well, it relies completely on Bernoulli's principle. You probably remember this from fluid mechanics. When the velocity of a fluid increases, its pressure decreases. It's a direct trade-off between speed and pressure. So by intentionally speeding up the liquid and measuring that drop in pressure, we can mathematically calculate the exact flow rate. Moving on to part 2, construction and working principle. A Venturimeter has a really distinct shape made up of 3 main parts. First, you've got the converging section. Here, the pipe diameter gradually shrinks, which forces the velocity to shoot up and, like we just said, the pressure to drop. Then the fluid hits the throat. This is the absolute narrowest point. Velocity is at its max here, and pressure hits rock bottom. Finally, it enters the diverging section, where the pipe gradually widens back out. The liquid slows down, and pressure recovers. Oh, and engineers keep that diverging angle intentionally small just to minimize energy loss. This whole physical setup essentially forces the fluid to obey the continuity equation. Basically, as the flow area decreases in that converging section, the velocity absolutely must increase so the same amount of mass keeps moving. It's kind of like putting your thumb over the end of a running garden hose. So how do we capture that data? To measure the pressure drop between the normal pipe and the constricted throat, we use a differential manometer. A simple U-tube setup containing a heavier fluid, usually mercury, connects one limb to the wide inlet and the other right at that narrow throat. Now, because the pressure at the throat is so much lower, it essentially pulls the liquid in the U-tube up on that side. This creates a measurable height difference, or differential head. By precisely reading this differential head, which you'll usually see marked as H, engineers get the exact data they need to figure out the discharge.
All right, part 3, deriving the discharge equation.
Let's look at the math. We start our derivation right here with the continuity equation. Area 1 times velocity 1 equals area 2 times velocity 2. This is our absolute foundation. It's fluid mass conservation. What goes in must come out. From there, we step it up to Euler's equation of motion. This equation helps us map out the precise relationship between pressure, gravity, and velocity in a steady flow. It mathematically proves that, hey, you can't change one of these variables without directly impacting the other. And here is where the magic happens. Integrating Euler's gives us the famous Bernoulli's equation. We apply this directly between point 1, the wide inlet, and point 2, the narrow throat. We're essentially balancing the pressure energy, kinetic energy, and potential energy between those 2 exact spots. So, after doing a bit of algebra, substituting the velocity, and tossing in a coefficient to account for minor real-world energy losses, we land right here. This beautiful, highly accurate final discharge equation. Q, the flow rate, becomes perfectly predictable. Just to make sure we're all on the same page, here's a quick breakdown of those variables. Once you know the fixed area at the inlet, A1, and the throat, A2, and you factor in gravity and your device's specific discharge coefficient, CD, the literally only thing you actually have to measure out in the field is H. That's the differential head from our U-tube manometer. Read H, plug it in, and boom, you instantly know your pipeline's flow rate. Section 4. Pros and cons. No device is perfect, right? On the pro side, the Venturimeter is incredibly accurate. Plus, because of that gently sloping diverging section we talked about, it has a very small head loss, meaning it doesn't waste pumping energy. It's great for massive pipes and requires practically zero maintenance. But on the flip side, they are expensive. They're bulky, demanding a lot of installation space, and they're difficult to manufacture. So yeah, they are completely uneconomical for small-scale plumbing. Finally, Section 5, Real-World Engineering Applications. So where are we actually putting these things to work? Well, you'll find them silently monitoring flow rates all over the place. They're in municipal water supply networks, massive hydroelectric power plants, petroleum pipelines, and even wastewater treatment plants. Basically, anywhere that demands precision monitoring of high-volume flow without stopping the system, a Venturimeter is likely doing the heavy lifting. To summarize all of this, the Venturimeter is an essential, highly accurate instrument. By leveraging Bernoulli's principle and the continuity equation, it transforms the invisible forces of pressure and velocity into actionable data that keeps heavy industry running smoothly. Fluid dynamics really is the hidden language of the built world. If you found this explainer helpful, definitely ask yourself, what other invisible fluid dynamics are shaping the engineered world around us right now? Keep observing, keep questioning, and I'll catch you in the next explainer.